In this lesson, we're going to introduce this concept called the mole, which is probably the centerpiece of a lot of how chemistry is discussed. So, to get us there, let's talk about how we count atoms. For example, let's say we have a balloon. This balloon is going to have a bunch of air inside of it, and it contains about 0.002% neon. But when it comes to that small percentage, it actually encompasses 5 times 10 to the 17th atoms. So if you can imagine, right? These balloons have all these air particles in them, but there's a ton of them. How do we know that there's billions and billions and billions of them? How exactly do we count them? Obviously, they're too small to count. So instead, we're going to kind of use a way to represent them. But first, let's present a problem. Let's say we want to make some compound like nickel oxide. Nickel oxide is composed of 2 elements, and they combine in a 1-to-1 ratio of nickel and oxygen, but we're going to try to do it without any leftovers. So all the atoms of nickel and all the atoms of oxygen will combine. Now, of course, like we said, we can't actually get a scoop of atoms and a scoop of atoms anyway by counting them because we can't really see them. So let's try this way. Instead, we'll use 10 grams of nickel and 10 grams of oxygen, which makes sense, right? 1-to-1. We're expecting both the reactants to be completely consumed in the reaction when there's no nickel or no oxygen left over. So it turns out, though, if you were to react them together, only some of that oxygen reacted. In fact, most of it remains unreacted. So only maybe 2% of the oxygen were reacted. So if you're looking over here, right on this right side, I kind of represented this. This is your nickel. Right, and then this might be your oxygen in red. And so if you think about them combining, right, you expect them to be matched up if you have it 1-to-1 like this. But as it turns out, afterwards, you have like these random unattached free oxygens that are floating about. Where exactly did they come from? Why is that the case? If I have a 1-to-1 ratio of 10 grams of nickel and 10 grams of oxygen, why are there any oxygen left over? So why is there so much of a difference between expectation and reality? So let's take a little bit of a closer look. We have to remember that nickel and oxygen atoms aren't identical. They're different masses. So a single nickel atom has about 10 times 10 to the minus 23 grams, so about 10 or so. And that's what we're representing here with blue. Whereas the mass of an oxygen atom is about 3 times 10 to the minus 23 grams. So again, ballpark it, it's about 3 and some times smaller than the nickel atom. So would 10 grams of nickel, therefore, have the same number of atoms as 10 grams of oxygen? And that's not the case, right? So if you're kind of thinking about this, it'd be like having, 100 pounds of bowling balls and 100 pounds of tennis balls. Would you have the same number of balls of each if you had, again, 100 pounds of each? Absolutely not, because the bowling ball is much heavier, so you'd have fewer of them in order to get 100 pounds. Same idea with nickel and oxygen. If I have 10 grams of nickel and 10 grams of oxygen, I have way more atoms of oxygen than I would for nickel because nickel is just a bigger, heavier atom. So that's when we instead use this idea of the mole. So using the mass does not always reflect the correct idea of amount, which is kind of frustrating because if you remember, right, one of the ways that we define mass is the amount of matter of substance, how much matter is in a sample. So using mass, again, isn't really helpful. In case you're wondering, there is actually a little bit of a side definition here that you can look at when it comes to mass. This is probably the better definition. Usually we have to take a physics approach to defining it. Whatever the case, mass isn't going to work out for us. So instead we use the mole. The mole is a quantity that represents the amount of matter in a substance. Really, probably the biggest takeaway is this relationship right here. 1 mole is equal to 6.022 times 10 to the 23 particles. Right. So the word particles is kind of a generic sort of placeholder. That should be replaced with whatever specific substance you're counting. So we're talking about atoms, molecules, electrons, grains of sand, coins, bananas, elephants. The number of particles, right, that are in a mole is going to be this value of 6.022 times 10 to the 23. By the way, that is definitely a relationship, so you can kind of use that as a conversion factor, which we'll see later on. The important idea is that this bridges mass, whatever we can measure as humans, because we can actually, use devices that can measure mass. It bridges mass and the number of atoms or particles in a sample. Of course, we can't count the atoms, so we're going to use something we can see, mass, to represent what we can't see, number of particles. Right. So again, please make sure we're looking at this idea of the numbers of them. So to kind of, again, give you some technical information here, quantity, the mole represents the quantity. The concept that's being measured is the amount of matter. The quantity symbol is N. So you might see this where, N is equal to blah, blah, blah. Let's just say arbitrarily 5.3. The unit is mole, but the unit symbol, which they really had to think hard about this one, is simply dropping the E and making it mole. So you might see something like N is equal to 5.3 mole, where N is the symbol that represents the quantity. And then MOL is used as the unit. This is also known as, or the 6.022 times 10 to the 23, that value is also known as Avogadro's constant, which is named for an Italian scientist and lawyer, Amedeo Avogadro. That's going to be a kind of alternative way to refer to it, but anytime you hear Avogadro's constant, you're thinking about 6.022. Just to make sure we kind of understand exactly what that mole is referencing, it's a way to count large numbers or to represent large numbers without actually saying that number. So, for example, if I say a pair of socks, we know that number refers to 2, or at least that term pair refers to 2. What about dozen? Well, a dozen refers to 12 without actually saying 12, right? A dozen means 12. Same idea with moles is that 1 mole represents 6.022 times 10 to the 23rd. So all these socks here. Now, again, the reason why we have to do that is because counting socks individually is a lot easier than counting individual atoms. So we can say pairs and dozens of socks because that's appropriate for the scale, but we have to use moles for atoms and particles because that's appropriate for its scale. You can also talk about 2 dozen socks, where that means 24 socks, without saying 24. You say just 2 dozen. Or you have 2 moles of socks, right? Or half a dozen socks and half a mole of socks. So they operate the same way. It's just that what the number is represented by is different, right? So dozen, 12, mole, lots. Now, to actually technically apply this information, we use something called the molar mass. Now, this word molar mass is going to be really nice. I'm going to ask this question quite a bit, and hopefully you'll get the hang of this, but is there a way that I can relate moles, which we just learned about, and mass? Is there a way that I can convert between moles and mass? The answer is yes. You can use the molar mass. It's right there in the word, molar mass, moles and mass. Let's talk about how this works. So since atoms of different elements have different masses, we can actually kind of maybe use very specific defined things that we've come up with as scientists a long time ago. So if atoms of different elements have different masses, thus a mole of atoms of different elements, right? So lots and lots of atoms of different elements should also have different masses, right? If I have 2 atoms of nickel, that's going to have a different mass than 2 atoms of oxygen. If I have a dozen atoms of nickel, that's going to have a different mass than a dozen atoms of oxygen. So we're again using this thing called a molar mass, which is the mass of specifically 1 mole, right? Defining it as 1 mole of a substance. So I'm saying there are 1 mole of oxygen atoms, there is 1 mole of nickel atoms. How much mass does that contain? That's what the molar mass means. The unit is grams per mole, and it uses that same value as the atomic mass of the element on the periodic table. So let's use this one right here. Bismuth is our example I'm going to look at. So atomic mass, AMU, is what we've already learned. That value right here, 208.98, yada, yada, yada. This right here is going to be 208.98, and actually that kind of rounds up. Yeah, let's use that, 208.98 AMU. That corresponds to the red here. But if we're talking about molar masses, we just do 208.98, in this case, grams per mole. And that's what we use for molar mass. Exact same number, just using the appropriate unit in the work that we do. So if we're talking about atomic mass, use AMU. If we're talking about molar mass, use grams per mole. But the number is still identical. Let's apply it. Let's see how this works. So applying molar mass, let's go and see this example. This one kind of already outlines that it's going to go between mass and moles, but let's make sure we understand why that works. So we have a sample of nickel, so the element here is provided as nickel, is massed at 10.0 grams. How many moles of nickel are in the sample? All right, so you were given a mass amount, right, that's the grams. We're being asked for the mole amount. So I'm being asked to relate mass and moles. What could I possibly use to relate mass and moles? Oh, I know, molar mass, right? It's right there. So I'm going to talk about this element nickel. I have to know to convert between mass and moles, I'm going to use molar mass. Well, where do I get the molar mass for nickel? Oh, I know. It's going to be the same as the atomic mass. Where do we get the atomic mass? If you look at the periodic table, the atomic mass is always listed there underneath your element symbol. So for nickel, it's 58.6934. Based on our rules from earlier, we're just going to do 58.69, and that's our atomic mass. But of course, we're talking about mole and mass conversion, so we're going to do it as 58.69 grams per mole. Of course, that is something that can be translated then as 58.69 grams of nickel per 1 mole of nickel. Okay, this is again how we take that molar mass and switch it into a conversion factor, which we can then apply to our given and whatnot. So our given is 10 grams, 10.0 grams. I'm going to label it nickel. And then I'm going to apply the conversion factor that I see over here into the spot. As you can see, grams is on top here, so I have to make grams also be on the bottom over here. So I got to take that conversion factor and flip it. 58.69 grams of nickel. On top will be 1 mole of nickel. All right. Thinking ahead, knowing that my grams of nickel will both cancel off, what I have left with, once I do the math, is moles of nickel, and that's exactly what the question is asking for. So at this point, I'm going to do a little bit of math. So my final answer for this one is going to be 0.170 moles of nickel. So 10 grams of nickel is actually going to represent 0.170 moles of nickel. Remember, 1 mole is like 6.022 times 10 to the 23rd. So 0.17 of those moles is how many particles there are of nickel in that 10 grams sample. All right, let's do it again for moles to mass. This time, right, it's already laying out the fact that it's moles and mass, but let's see what the problem gives us to know that. A sample of oxygen atoms is determined to have 0.625 moles of atoms. How much mass, right, that's the question, how much mass does the sample contain? Well, again, I'm being asked to relate moles and mass. Is there something that I have that can relate moles and mass? Oh, I know, molar mass. So with molar mass, right, that's the same as the atomic mass of oxygen. I can find that on the periodic table. Going back over here, oxygen, zooming in, 15.9994. That, of course, kind of get rounded to 16.00 grams per mole of oxygen. As a conversion factor, that's 16.00 grams of oxygen per 1 mole of oxygen. Right, just literally translating this grams per mole into grams per mole. Apply the given value, 0.625 moles of oxygen. The conversion factor in this case can be stuck in as is, right? No need to flip this conversion factor, 16.00 grams, and then 1 mole of O. Right, looking ahead, you're going to cancel off moles of O, moles of O. What you're left with is grams of moles, or grams of oxygen, which provides you 10.0 grams of oxygen. Okay? So that's how you can apply molar mass. In a similar vein, right, we can also apply Avogadro's constant. Let's see how this one differs a little bit. This one relates moles and particles, right, as you can see here in this header, but let's kind of make sure we understand what the question is asking for to know that we apply this. This time it's asking for how many atoms of nickel are in 0.170 moles. Right, so now we're given a mole amount, and we're being asked about a particle. Atoms are really tiny particles, right? So we're being asked to relate moles and particles. So what I can use is Avogadro's constant, because that tells me that for every 6.022 times 10 to the 23 atoms of nickel, that's actually equivalent to 1 mole of nickel. So right there I can go ahead and apply this, and I'm given 0.170 moles of nickel. I can use this conversion factor appropriately. This time I don't have to flip it because moles of nickel is on the bottom here, moles of nickel is on top, so I go and stick it in as is, 6.022 times 10 to the 23rd atoms of nickel for every 1 mole of nickel. That's basically what that's referring to. Doing a little math, you end up getting 1.02 equals 1.02 times 10 to the 23rd atoms of nickel. Kind of in the same vein here, right? The question, the next bullet point, how many moles, so the question is asking for moles, are in 3.76 times 10 to the 23 atoms of oxygen. I'm given a particle amount. I'm being asked to figure out the mole amount. Apply Avogadro's constant. Now, I'm not going to rewrite this conversion factor up here because, frankly, moles and atoms, if you notice, I didn't have to look at the periodic table. That relationship, that Avogadro's constant, is not specific to an element. It's just, broadly speaking, number of particles. So in this case, when I have oxygen, it doesn't change the value of the atoms that might be applied to nickel. Because, again, a mole is defined. It is just a group of particles. So in this case, I'm going to go ahead and stick in 3.76 times 10 to the 23 atoms of oxygen, right? That's my given. And then my Avogadro's constant, I can see here that if I want to flip it upside down or put it as is, I can do that. This time I flip it because that number has to be on the bottom. And then, oops, instead of writing nickel, right, we're doing this one specific to oxygen, so I write O there. And then for 1 mole of oxygen up top. And then do some math. You get 0.624 moles of. So to wrap it up and kind of bring it back to the original question is, how do you kind of handle this? Well, why do 10 grams of nickel and 10 grams of oxygen have leftovers, even though the formula itself suggests a 1-to-1 ratio? That's because gram amounts don't accurately represent the number of particles that are there. If we want to make sure that there's no leftovers, that means we have to make sure that each particle of nickel, right, each atom of nickel, has a corresponding atom of oxygen. But unfortunately, with 10 grams of each, grams don't reflect the number of particles. So instead of saying maybe 10 grams of each element, 10 of what unit might provide the desired result? Well, I mean, 10 maybe moles, right? We've spent this time talking about it. You could sit there and say, okay, 10 atoms of each, right? So 10 atoms of nickel, 10 atoms of oxygen. That's great and all, but in a more practical sense because atoms are, too small and we work with way more atoms than just 10 at a time. It might be easier, in fact, to say 10.0 moles of each of them would be much more capable of providing the result that you want, right? So instead of saying 10 atoms, 10 moles, right? 10 groups of atoms. Finally, how many grams of nickel and how many grams of oxygen would be needed to make this happen? Well, if you go back to the previous problems, it actually works out to where you need, if you have 10 moles of each. So instead of saying 10.0 moles of nickel, doing a little bit of quick math, which again you can use from the previous examples, or at least same work, would be 587 grams of nickel and 10.0 moles of oxygen. If you use that mole amount, you'd actually need 16.0, nope, just kidding, that'd be, try that again, 160 grams of oxygen there. And so these amounts would actually end up giving you the desired result, where each atom of nickel, each atom of oxygen would be paired, and so that you'd have no leftovers. That's a lot different than saying 10 grams of nickel and 10 grams of oxygen. Finally, for this lesson here, we're going to introduce this idea of the mole map. This one is going to involve a lot of parts that won't be necessarily relevant for this particular lesson, but let's go ahead and focus on just the top part here. We're going to disregard the bottom for now. So one of the things that you'll find is that this is going to be a nice way to organize how we interpret the work, right? So if we have a substance here, we know we potentially have a mass, we have a mole amount, or even a particle amount that we're given. So anytime you're given one of them, you can solve for the others. For example, right, if you're given 10.0 grams of nickel, you're being asked for the mole amount of nickel. Well, again, what can I use? I know that I have the molar mass right there. That's going to be used as a bridge between mass and moles to get me from grams of nickel to moles of nickel as a potential example. That works for any other possibility, right? For moles to particles, same thing. If I'm given a mole amount, they want to know how many atoms there are, I would use Avogadro's number. Vice versa, particles to moles, I'd still use Avogadro's number. You just have to use the conversion factor in the appropriate way, whether you flip it upside down or not. And of course, as you can imagine, if you are given particles, you can also then conceivably be asked to figure out mass, which you then have to go from particles to moles, and then from moles to mass in a two-step process. Okay, that'll do it.